Back to the linear algebra session again. We are going to discuss to the linear independence of vectors and span of a set of vectors. We will solve problems on checking whether a set of vectors are linearly independent or not, and also we will find basis for the span of a set of vectors. We begin with by recalling the concept of vector in the context of matrices. Recall that recall that by a vector we mean by a vector we mean either a n by 1 matrix, that is a column matrix, or number 2, a 1 by n matrix, that is a row matrix, or number 3, a n tuple x1, x2 and so on, xn having n components. Also, by vector addition or multiplying a matrix, rather vector, by a scalar we mean addition of the vectors component wise or multiplication by the scalar component wise. For example, if we add the matrices or vectors, say 1, 2, 3 with 3, 1, 2, it is same as 1 plus 3, 4, 2 plus 1, 3, 3 plus 2, 5. Or if I multiply this vector by the scalar 4, it means it is 4 into 1, 4, 4 into 2, 8, 4 into 3, 12. Or if I multiply the matrix 1, 2, 3, it is same as 4 into 1, 4, 4 into 2, 8, 4 into 3, 12. This is how we are going to add two vectors or multiply a vector by a scalar. Say for one more example, if I give adding tuples, say if I add 1, 2, 3 plus 3, 4, 5, what we are going to get? We are going to add component wise 3 plus 1, 4, then 2 plus 4, 6, then 3 plus 5, 8. So this is the resultant vector, or sum of these two vectors. We use small letter v to denote a typical vector. Remember, by vector we mean either a n by 1 matrix or a 1 by n matrix or a n tuple. So if I say V is a vector, so you bring the picture of either of a matrix of order n by 1 or 1 by n or of a n tuple into your mind to imagine this vector V. Now we are going to introduce the concept of linear combination. A vector V is said to be a linear combination of the vectors v1, v2, vn if there exist some scalars. So here by scalar we mean real numbers such that v is equal to alpha 1 into v1 plus alpha 2 into, so there exists some scalars, say alpha 1, alpha 2 and so on, alpha n, such that v is equal to alpha 1 v1 plus alpha 2 v2 plus and so on, alpha n vn. For example, take v is equal to 1, 2, 3, v1 is equal to 1, 0, 0, v2 is equal to 0, 1, 0, and v3 is equal to 0, 0, 1. Observe that 1 into v1 plus 2 into v2 plus 3 into v3 is equal to. Now what is 1 into v1? We have to multiply each component of v1 by 1. So it is 1, 0, 0. What is 2 into v2? We have to multiply each component of v2 by 2. So it is 2 into 0, 0, 2 into 1, 2, and 2 into 0, 0. And then v3 we multiply by 3, it means it is 0, 0, 3. So when we add them, what we are going to add? We are going to add component wise. So first component is to be added. So 1 plus 0 plus 0, so that is 1. Then 0 plus 2 plus 0, that is 2. 0 plus 0 plus 3, that is 3. And this is nothing but v1, v. So therefore what we got? V is equal to 1 into v1 plus 2 into v2 plus 3 into v3. So we can say that is V is a linear combination of v1, v2, v3. In similar way, you observe that if I take V to be the matrix, say 2 minus 4, 3, say V1 to be the matrix 1, 0, 0, V2 to be the matrix 1, 1, 0, and V3 to be the matrix 1, 1, 1. We can write V to be equal to can write V as 6 into V1 minus 7 into V2 plus 3 into V3. I'm leaving this as an exercise for you. So therefore, V is a linear combination of V1, V2, V3. Now we are going to introduce the concept of linear dependence. So linear dependence. A set of vectors say v1, v2 and so on vn is said to be linearly dependent if one or more vector in the set is a linear combination of the remaining vectors. So what that means? So you have one vector here or maybe more than one. So we are happy if we have one. So we are having if we have one member of this set which is a linear combination of the remaining members of the set. For example, if we take V is equal to say 3, 4, V1 is equal to let us call it V1 is equal to 3, 4, V2 is equal to 1, 0, and V3 is equal to 0, 1, then the collection V1, V2, V3 is linearly dependent. We write LD for linearly dependent short because if you observe carefully, we can express V1, one of the members of this set, as a linear combination of the remaining two, V2 and V3. So we can write V1 as 3 times of V2 plus 4 times of V3. Since one of the member of this set is a linear combination of the remaining vectors V2 and V3, so this set of vectors is linearly dependent. One quick remark we will write here, and one quick remark we'll write here is that any set of vectors containing the zero vector is linearly dependent. Quickly we can see this through this example. So consider the set. So zero vector, I am denoting zero vector by theta, and some other vector, say v1, v2, and so on, vn. Observe that this zero vector is 0 times of v1 plus 0 times of v2 plus and so on 0 times of vn. Remember, these zeros are scalar zeros. This is theta, zero vector. So the result follows. Any zero vector can be expressed as a linear combination of any set of vectors. So that's why if zero vector is a member of a set, then that set is linearly dependent. So you can note this as a quiz question. If I have a set of vectors and zero vector is a member of that set, then that set is always going to be linearly dependent. Now, linearly independent concept. A set of vectors is said to be linearly independent if it is not linearly dependent. So a set of vectors is said to be linearly independent if it is not linearly dependent. We now write steps to check whether a set of vectors is linearly dependent or not. So we'll write down the steps. So process to check linear dependency or independency, you can say. First, to check the vectors v1, v2, and so on, vn, for linear dependency, we follow the following steps. Number 1, form a matrix A in which ith row has the entries of the ith vector vi. Step number 2 is reduce A to row echelon form. Number 3, find rank of A. And last step is if rank of A is equal to number of vectors. So in this case it is equal to n. Then the vectors are linearly independent, otherwise the vectors are linearly dependent. So what we have to do, if you are given vectors v1, v2, vn, so construct the matrix A in which each row consists of the entries of the vectors. So we will be having n rows for n vectors. If we are given n vectors, then reduce the matrix to row echelon form. From row echelon form, you can get the rank of the matrix. What is rank of a matrix? It is the number of non-zero rows in the row echelon form. So get the rank of the matrix A, then compare rank with the number of vectors given. So here we are given n vectors. So if the rank of A is equal to number of vectors, so that is n, then the vectors are linearly independent. Otherwise, the vectors are linearly dependent. Show that, so let us take this example, show that the vectors, say 1, minus 1, 1, 1, 0, 1, and 0, 1, 2 are linearly independent. So that the vectors 1, minus 1, 1 and 1, 0, 1, 0, 1, 2 are linearly independent. Solution. So what we are going to start? We are going to form a matrix A. First step, form a matrix A with the entries of the vector as row. So first vector row is 1, minus 1, 1. Second row is second vector. So it is 1, 0, 1. Third row is 0, 1, 2. So next step is to reduce this matrix to row echelon form. So how we can do it? So here this is the first pivot. So if it is pivot, below this all entries should be 0. So we have to apply the operation R2 goes to R2 minus R1. So that makes it 0. This is already 0. So the reduced matrix is 1, minus 1, 1, then 0, 1, 0, and then this is 0, 1, 2. So this is my first pivot. So this is going to be the second pivot. So this entry need to be reduced to 0. So we'll apply the operation R3 goes to R3 minus R2, and that makes it 1, 0, 0, minus 1, 1, then 1, 0, and this is 1 minus 1, 0, 2 minus 0, 2. So we got this is first pivot, this is second pivot, and this is going to be the third pivot. So which is in row echelon form. So therefore rank of A is equal to number of non-zero rows here, so that is equal to 3. and that is equal to number of given vectors. So how many vectors we are given? 3 vectors, 1, 2, 3. So the given vectors are linearly independent. So if this rank is less than the number of given vectors, then these vectors will be linearly dependent. So here we are getting rank to be equal to the number of given vectors. So that's why they are linearly independent. Now let us give the concept of span of a set of vectors. Span of a set of vectors. So what we mean by span of a set of vectors? By span of a set of vectors, as we mean the collection of all those vectors which is a linear combination of some vectors in S, and we use this notation, writing S in between this, to denote the span of S. Now, example, if S contains only one vector, say 1, 0, then what is S span of S? This is the collection of all those vectors whose coordinate is any arbitrary coordinate. So it is X can be any real number, because you see any such vectors x comma 0 I can write as a linear combination of the vector 1 comma 0. So this vector is a linear combination of some vector in S. So this is a member of the span. So it means any such vector going to be span of S. One geometrical interpretation of this is that if I take this vector 1 comma 0, remember this is a vector at a distance 1 on x-axis from the origin, 1 comma 0. So any multiple of this will give me a vector on x-axis itself. So x comma 0 is a multiple of 1 comma 0. So that's why it is a vector from the x-axis itself. So the span of this single vector actually the whole x-axis. Next example I give you S to be 1 comma 0 and 2 comma 0. Notice that in this case also span going to be x comma 0 such that x is in R. We are not actually getting anything extra. If I take any vector x comma 0, so it is a linear combination of 1 comma 0. So x into 1 comma 0, or we can also write it as x by 2 times of 2 comma 0. So I can either consider as a combination of 1 comma 0 or 2 comma 0. So that's why we are not getting anything new here. We are getting the same collection here as well. So what is the difference between these two sets? So see, the singleton set S also generates this set, and this set having two vectors also generate the same set, or the span for both the sets S, or let us call it S1. span for both the set S and S1 are going to be same. So if I want to remember a member that generates this set, instead of remembering both this member, I will remember one 0 only, because this is enough to generate this whole set. And here the concept of basis comes. So we'll say that basis of this set contains only one vector. If I write this, so this is a redundant vector for me. If I drop it, still we will be able to generate the same set of vectors. So I'm refer the definition of basis in the lecture note for more clarity. Now, how to get the basis of a span of a set of vectors? So that is what we are going to discuss now. Example, find a basis for the span of, say, 1 comma 2 comma 3, then 1 comma 1 comma 0, then 0 comma 1 comma 3. So what we are going to do for finding this basis? Again, we are going to write a matrix A with each of these vectors as one row. So 1, 2, 3, 1, 1, 0, and then 0, 1, 3. We reduce it to row echelon form by applying appropriate row operation. So here the first non-zero entry is 1. So the row operation I have to apply to make this entry 0. So it is R2 goes to R2 minus R1, and that reduces it to 1, 2, 3, 0 minus 1 minus 3, and then 0, 1, 3 here. So this is first pivot for me. This is the second pivot for me. So I'll apply the operation. R3 goes to R3 plus R2 to make this entry 0. So the resultant matrix going to be 1, 2, 3, 0 minus 1 minus 3, then 0, 0, 0. So we got a pivot here, we got a pivot here. Last row does not have, will not have any pivot because it is a 0 row. So this is in, which is in row echelon form. Now we will note the non-zero called rows here, and that will give me a basis for this. So therefore a basis for the span of the given vectors, is, first I will take first row and form a vector 1,